Hello everyone, welcome back. Today in this video we're going to look at NumPy, the library NumPy, and why is it useful. So today in this video the agenda is to look at to understand dimensionality and shape of NumPy arrays, to see what are all the operations that you could perform on NumPy arrays, and we're going to see the concept of broadcasting in NumPy, and we're going to look at a few more NumPy methods that are there in the library. All right, so let's get started. NumPy is a library used for numerical operations related to um, linear algebra and calculus, which is highly used in machine learning and data science. So it is very convenient. It is very convenient to perform mathematical operations using NumPy arrays. So let's look at the first topic now. So first of all, I'm just importing NumPy as an alias of NP. So this is a convention that you can use. You can import libraries and you can give a alias name. So instead of using NumPy everywhere, you use you try to access a method or a function in that particular module. You can simply use the alias NP instead of writing the entire NumPy, and you can still have access to all the variables and methods that are there in that particular library or module. All right, now let me just import that. And in NumPy, you have arrays. So basically, in NumPy, you have arrays. So they are called as NumPy arrays. NumPy arrays are nothing but normal arrays which are optimized to perform mathematical operations on them. So I'll just show you how. So I have a simple list here or an array. I have a simple list 1, 2, 3, and I'm creating a NumPy array out of it. And the way you create it is call np.array and pass in the list into the arguments, and it will return a NumPy array of that same particular value. And if I try to print out the type of x1, it should give me that it is a NumPy array. And if I try to print x1, it should print out the NumPy array x1. There you go. So it's showing that it belongs to the class NumPy uh, and dot nd array. So nd array stands for n dimensional array. So we have a concept called as dimensions here. I'll just show you what that means. And we have the NumPy array being printed out over here. All right. So here I'm trying to show you something. Okay. So what I'm doing is I'm taking the NumPy array x1 and I'm trying to print the dimensions of it. So every array has a dimension. So basically these are called as vectors. So we have a property called as dimensions. So basically is to put it simply, you can think of them as a number of nested brackets that we have in the NumPy array. So you see only we have one level of nesting brackets. So we have a one set of brackets that are there in this particular array. So that dimensionality should be 1. And if you print out the shape of the NumPy array, we'll get the shape of each and every dimension. So if we have only one dimension, we'll get the shape of only one dimension. If we have two dimensions in a NumPy array, we'll get the shape of the shapes of all the two, like both the dimensions of our NumPy array. So this will make more sense as we look at some examples. So you see we have the dimension of the NumPy array as 1 because we have only one level of nesting going on here. And if I try to print out the shape, I'll get the shape as 3, comma. Okay, so since we have only one dimension, I'm getting only one number, which is the shape of the dimension. So you can think of it like this. Okay, so we have only one nesting of list, one nesting of brackets, and inside that we have three elements. So that means that we have only one dimension, and that dimension has three elements. Hence, the shape is 3. So that is what this means. And to print out the dimension and shape, we use this properties. So for dimensions, we print out ndim, which stands for n dimensions. And for shape, we just use a property shape dot shape, which will return the shape. Now let's look at an example of two-dimensional array. So here I have a list of lists. So in this, I have a outer list which has elements, and each element is a list which contains one element each. So you can take a better look at this comment. So we have an outer list which is this one, and inside that I have three elements, and each element is a list, and inside that we have a value, right? So here we have two dimensions to it because we have two levels of nesting, right? So we have a outer list and we have inner list in it, and we don't have any further inner nestings of brackets in there. So the dimension is 2. And if you look at the size, if you try to print out the size of this numpy array, we should get the size as 3 comma 1. Why is that so? This is very simple. You just go from the outermost nesting of brackets, which is this one, and you count the number of elements inside that. So in the outermost nesting of brackets, I have 3 elements, which is this list, and this list. So I have 3 elements. So the size of my first dimension is 3, and the size of second dimension is, you go inside, you go to the inner dimension by one level. All right, so the inner dimension, which is these inner lists, have one element each. So which means that the size of the second dimension is 1. So it will make more sense if I try to print the numpy array out. So let's just run this cell. So there you go. You can look at it as some sort of matrix as well. So just like a row matrix, it has 3 rows and 1 column, or you can count it in terms of brackets. So in the outermost bracket, which is the first dimension, we have 3 elements, and in the innermost bracket, which is the second dimension, we have 1 element each. So which means the second dimension size is 1. So likewise, we can see here dimensionality of the numpy array is 2. The shape of the numpy array is 3 comma 1. 3 is the outermost, the first dimension size, and 1 is the second dimension size. And let's look at another example now. We have a same thing going on here. Um, we have same thing going on here, but I'll just explain the resize operation to you after a while. Just don't pay much attention to it. I'll just explain it to you. Let me just comment that out. Right, and let's run that. Okay, now you see we have another example. This time we have 2 levels of nesting again, which is outermost level is this one, and the innermost level is this one. We have 2 dimensions to it. Size of the dimensionality of an umpire is 2. And what about the shape? So outermost dimension, which is the first dimension, we have 3 lists in it. So the shape of first dimension is 3, and in the innermost, in the second dimension, we have 3 elements each. So the first list contains 3 elements, second list contains 3 elements, and third list also contains 3 elements. So likewise, we have the second dimension shape as 3. So that is how you count the dimensionality of your NumPy arrays, and also the shape of your NumPy arrays. Or you can assume it as some sort of matrix, and you can just count the rows and columns, which is 3 rows and 3 columns, which is 3 by 3. All right. So that is how they work. And now I'm going to show you the resize operation. So just like you can, play around with your matrices in mathematics, you can also play around with NumPy arrays in Python. Let me just put those in another cell and run those. So if you see, we have we are trying to uh, resize the matrix that we have here x2 into a shape of a 9 by 1. So we have a 3 by 3 matrix which is of size which is of 3 size 3 by 3, and we have 9 elements in it, and I'm just trying to resize it into a column matrix which will have 9 elements in the first column. So that so you can simply use a resize operation where the and provide the shape of the new matrix, which is 9 size of the first dimension and 1 size of the second dimension. So that is how the resize operation works in NumPy. Now we have another example. This time we are going to look at a matrix of 4 dimensions. So I have 4 levels of nesting here. So the first level is this one. Second level is this one. Third level is this one. Okay, so we have 3 levels of nesting, which is the dimensionality 3. Okay, so not 4. We have three-dimensional NumPy matrix here, NumPy array. And the size of the NumPy array is calculated in the same way as I explained to you. So we have the outermost list in which we have 2 elements in it, right? So the size of first dimension is 2. And we have the second outermost list which has 2 elements in it each. Hence we have the second dimension as 2, and for the third dimension we have 3 elements in each list. Hence the size of the third dimension is 3. All right, simple enough. and that is how this dimensionality and shapes actually work in NumPy. Now let's look at some of the operations in NumPy arrays. So I'm just creating two NumPy arrays or 3 by 3 matrices, you can think of it, and called A and B, and I'm just printing them out. Now you see we have two matrices or NumPy arrays called A and B. Now we can perform all the operations that we can perform on matrices, right? So these are simply nothing but two matrices, and we can perform matrix addition, matrix subtraction. Let me just run those. Matrix addition A plus B, which will add the corresponding elements, which is 10 plus 11 is 21, 9 plus 22 is 39, and so on. So all the corresponding elements are added up. Same with the subtraction, where all the corresponding elements are subtracted. 10 minus 21 is, 10 minus 11 is minus 1, 9 minus 22 is minus 13, and so on. Same with the multiplication. This multiplication doesn't do matrix multiplication, but it actually multiplies element wise. So 10 times 11 is 110. There you go. And 9 times 22 is 198. So this multiplication operation does what it does is that it multiplies element wise in both the matrices. Similarly with the division, element wise division and element wise XOR operation. Now, to perform matrix multiplication, you have to use the @ symbol. This actually does a matrix multiplication. And as a matrix multiplication rule goes, for multiplying two matrices, the number of columns in the first matrix should be equal to the number of rows in the second matrix. So if you go back and brush up your linear algebra topics, you will find this rule saying that the second dimension of the first matrix should be equal to the first dimension of the second matrix. And the resultant matrix will be of size 3, 3, which is the remaining two dimensions. So if I run this, I'll get the result of matrix multiplication of A and B, right? And just like a matrix, you can simply transpose a matrix as well. So I have the matrix A 10, 9, 8, 7, 6, 5, 4, 3, 2. And if I do dot T, I'll get the transpose of A, which is 10, 7, 4, 9, 6, 3, and 8, 5. So basically transpose operation is nothing but uh, switching up of rows and columns and rows. So basically this 10, 9, 8 row is replaced by is switched as a column, which is here 10, 9, 8, and the 7, 6, 5 is also take like replaced from a row to a column, which is 7, 6, 5 over here, and likewise with the third row as third column. Simple enough. Now here is another example of transpose operation. So I have a row matrix which is 1, 2, 3, and I'm just trying to print out the shape, which will give me 1, 3. The size of first dimension is 1, and the size of second dimension is 3. So this should print out 1, 3, and I'm just trying to transpose it and save it in a new variable, and I'm trying to print out the shape. So if I transpose a row matrix, I should get a column matrix. So let's just see. There we go. We have a row matrix of size 1, 3, and if I transpose it, I'll get a column matrix of size 3, 1. So that is how transpose operation works. And here is another operation that I wanted to show you. This is called as ravel. So what it does is it takes a matrix, any matrix or any NumPy array, and it spreads that out. What it does is it basically lays them out. From a high dimensional view, it brings them down to a single dimension with all the numbers rolled out. So that is how the ravel operation works. Now moving on, we have the determinant. So just like you can calculate the det of a matrix, you can also do this in NumPy. You can use np.linalg, which stands for linear algebra dot det operation on any matrix that you want to calculate a determinant of. So this will give me the det value, which is the determinant value of a matrix. Similarly, we can also calculate the inverse of a matrix, which is a linear algebraic operation on matrices. And if you still remember your linear algebra classes, you might remember that multiplying any matrix with its own inverse will give you uh, an identity matrix. An identity matrix is a matrix in which all the elements on the diagonal are 1 and the rest of the elements are 0. Now it should make pretty much sense if I run this. There you go. So we have the matrix B over here, and we have the inverse of the matrix B over here, And when I matrix multiply A and B, I'm getting an identity matrix. Don't mind the minus symbol on zeros because that doesn't matter. We have the values 1, 1, 1 on the diagonal, and the rest of the values are 0. So that is an identity matrix. I'm just rounding the decimal values to 0 decimals so that we have a clear picture of an identity matrix. Otherwise, we'll be left with some decimal values after the point. So don't need not worry about too much about that. So that is how the inverse operation actually works. So the function is np.linalg.inverse. All right, and similarly we have a few more functions, like we have tan operation, which is a trigonometric operation. We have sine operation, we have log operation, we have exponential operation, which is e power operation. So all of these are element wise operations, which means they are actually perform this operation on each and every element of the matrix. So each and every element of the matrix has been logged and the values are over here. Each and every element of the matrix has been performed as sine operation, and their values are here. Similarly with the tan and exponential operation. So those are some of the operations that you can perform on NumPy matrices, NumPy arrays. Now we are going to look at broadcasting concept in NumPy. So in broadcasting, so basically the concept here is that before understanding the concept, let's look at an example. Then it will make more sense. So I have three NumPy arrays. First one is a 3 by 3 matrix. Second one is a row matrix, and third one is a column matrix. And I'm just printing them out here. So we have a 3 by 3 matrix, we have a row matrix, and we have a column matrix. Right now, if I try to add, so I'm taking this 3 by 3 matrix A, and I'm trying to add a single digit number, a simple integer number, which is 10, to this entire matrix. So what will happen is that this 10 will get broadcasted, which this 10 will be conveyed, which will get operated, will get added to each and every element of the matrix, and the result will be returned. So basically this 10 is broadcasted to each and every element in the matrix, and the value is returned. There you go. So for 1, 2, 3, 4, 5, 6, 7, 8, 9, the 10 is added and we get 11, 12, 13, 14, 15, 16, 17, 18, 19. So the 10 is broadcasted over there. Now another example of broadcasting is I'm taking this 3 by 3 matrix and I'm adding the X, which is a row matrix. Okay, so if I add this row matrix to this 3 by 3 matrix, what will happen is that this row will be added to each and every row inside this matrix. So the 1, 1, 1 will get added to 1, 2, 3. This one will get added to 4, 5, 6, and this row will get added again to 7, 8, 9. So this will look something like this. So basically the this row matrix is broadcasted to the entire 3 by 3 matrix. So there we go. Every element is added with 1 and we get the result. Similarly with the column matrix, if I try to add this column matrix to this matrix, 3 by 3 matrix, this will get broadcasted to each and every column inside this matrix. And you can verify the result. Now here is an interesting thing. If I try to add x and y, which is the row matrix and the column matrix, I will get, so the better explanation will be this picture. So if I'm taking a row matrix and a column matrix, this will get broadcasted to one another and will get a 3 by 3 result, 3 by 3 matrix as a result. So this will get repeated 3 times and this will get repeated 3 times, and both will get added as a 3 by 3 matrix and will get a result. So that is how broadcasting works in NumPy. Let's just see the result. There we go. We have a 3 by 3 matrix with all the values as 3. If you can cross check that by adding both of these NumPy arrays. And now let's look at some more NumPy methods and wrap up the video. Now, here is another method called as arange. This works similarly to the range function in Python. Basically, what it does is that it gives the range values or the 0 to 9 values, and we can resize them however we want. Let me just run that. There we go. The numpy.arange gave me 0, 1, 2, 3 up to 9. And then I can resize them. Since this is a numpy array, I can resize them however I like. So I'm resizing them into 3 by 3 matrix. Since there are 9 elements, I'm resizing them into 3 by 3 matrix. Now, here I have another method, This is zeros method. If I call np.zeros and I pass in a shape in it, what it will do is it will return a matrix of this size with all zeros in it, right? Something like this. And similarly, we have another function called as ones, which works in a similar way. Instead of filling it with zeros, we have all the ones in that matrix. And we have the I function, which stands for identity function. So basically, this returns the identity matrix of size 5. There we go. We have identity matrix of size 5 in which all the principal diagonal elements are 1 and all the other elements are zeros. And finally, I have this function for you, random function. So let's say you want to generate a matrix of size 2 by 2 with random numbers in it, and the random numbers are between 0 and 1. Then you can simply use this np.random.random and pass in the size, and you'll get a function with random values between 0 and 1. And that is all about NumPy that you might want to know. And if you want to learn about more functions that are there in NumPy, you can go to the NumPy documentation. Just go to web search and search in NumPy, and you can go to numpy.org. And here you can find all the documentation for all the methods that are there in NumPy. All right. So that is it for this video, and I'll see you in the next video. Thank you.